Hey guys, I'm back with a second video. I'm actually going to try and squeeze in a second video today so we can get through this. So next is on the chopping block. Rods, choosing rods. What rods you're looking for? Why do you need them? And what's the purpose of all this? So again, going to look at our rods. There's a factory ones we have here for the 4B11T. Now those guys, they did do the ARP 2000 upgrade, which is good because normally when a rod fails, it's not the rod, it is the bolts that fell because the tensile strength. So factory, you got your stretch bolts. They are basically torqued to yield. So yield basically is the point where the elastic part of the metal stops and it starts to bend permanently. And these ARP 2000s are a higher tensile. I think at 8.9, 10.1, and 12.9, 12.1. I always forget the numbers, but 10, 11, and 12, and then you'd have necking forming, causing deformations and that. But these bolts are actually usable. I don't see any necking on it. So necking would be if you see any hourglass shapes form in there, that's necking. However, I don't think that'll be the case. So with these ARP 2000 bolts, they go according to bolt length. That's going to be your deformation, because the more you torque this, it's going to stretch a bit. If it's too much, you're going to deform a bit. Elasticity and that. Okay, we'll get to that in a bit. So here are factory rods. I think this is made from a iron alloy of some kind. I'm not sure which one. Could be just a forged metal rod. Not very pristine. Well, it's not pristine. It's a good quality metal, but as you can see here, we've got some markings there. We've got some damage here, so we decided we're just going to replace the rods and that. So you can see you've got markings there and all that, so we had to work around that and just replace them with new ones. Let's get one that's a bit better. So something like that probably would happen from lack of oil flow, over revving, dropping the clutch, things like that. So this one here has a better view, so I want to see if I can check out. So with your connecting rods, obviously you got your top end, you've got your bottom end, you have, this one does not have oil feed to the top of the piston, but sometimes you would have a small hole there on the bearing that would feed oil through to the top, as you would have a little hole there. I think that's for the oiling, cooling, could be a few different things. But yeah, and then you have your brass bushing over here, and you would have your engine bearings over there, right? Straightforward. So let's jump over to the performance rods. Again, wearing your nitrile gloves so you don't get your grease and things over it, forming deformations and corrosion and wear and tear. So similar looking design, and you would think that this rod is actually heavier than the rods, because I mean you have a bigger area, right? So it must be heavier. So let's check that. So we're going to first test our factory rod here. 570 grams on that, and then let's grab another one here just for like demonstration purposes, right? Let's get a 569, so the weight's not even the same. Try not to knock your rods on things when you working with us. And yeah, so let's check this one. So that was 570. I forgot the number now, sorry guys. Yeah, 570. All right, so let's see how much is this one going to weigh. Probably like what, 900 grams, and it doesn't. 586. It's 16 grams lighter than this. So for comparison, the weight difference, your piston rings that we measured earlier was 22 grams. The weight difference is less than your piston ring. So how is that? How can this be 1,000 horsepower capable rod and this other one just goes up to about 450? So the guys on the forums and the groups and things, they've pushed about 450 to 500. One of the guys claims he runs 1,000 on stock internals. I think he refers to stock crank, because yeah, one of these things. That so all that comes down to inertia basically. So what exactly is inertia? So inertia is resistance of, well, for this case we're going to be looking at mass moments of inertia. Was bending moments of inertia, I think was the correct word. I'm a bit rusty. It's been a few years since I left university. So yeah, so we have resistance to bending. So this has to do with the shape of the rod. So why is an H-beam like that in this configuration and not like that? So let me see if I can get a clipboard out here to show you guys what's going on. Okay, let's quickly do some lessons on inertia. So basically, if you were to think of, say, a bicycle wheel, something like that. I know we're doing cars, but work with me for a bit. So that's a bicycle wheel. You have a nice little rim out there, and then your axis is there. Now, if you were to have just like a think about a lawnmower wheel that just has like a little tiny little disc. It's solid, but it's a lot smaller. Let's say this weighs 1 kg, and this one weighs say 2 kgs. Oh, let's make it 1 for the same argument's sake. If you have angular momentum on that, this one is going to be so much easier to stop than that, even though they weigh the same. So why is the mass different? So it comes down to inertia, which means the further the mass is, the center of mass of rotation is from the center here. Let's say that is like 10 centimeters. I know like only fashion design work in centimeters, but just work with me here just for demonstration purposes. And say this is, what's it, 100 centimeters? I don't know what a bicycle wheel size is, 100 centimeters. This is going to be far harder to stop or accelerate through grabbing onto the wheel there than this one is. So let's apply that to pistons. So in a piston, you have your crankshaft rotation, which is here. I'm not going to draw a crankshaft. So that's your rotation of your crankshaft. And let's do another one here. So if you have your cross section here, so let's say you were to take this con rod here. Let's say we take our nice nether rod here, we cut it straight in half. It's going to have that H-beam configuration, also I-beam configuration, right? So it's going to look like that from the top. It's not a very accurate drawing, but that. And then obviously with our factory rod, we have the same thing, but it's a little bit closer. So if you were to look at that, comparing this size there to this size over there, right? So that's more or less to scale, I guess. The amount of mass that you have away from your center here is a lot more than the amount of mass you have from your center here, tiny little bit. And that is basically the whole idea of what inertia is. It's resistance to deceleration, it is resistance against bending, it's resistance against so many different things, that basically comes down to that in a nutshell. So let's ask, so why would you want to get an I-beam versus an H-beam? Now, they have different applications. If you really dig far enough, you will find it. That your H-beam applications, I draw it up a little bit bigger here, a little bit exaggerated. Here from the shape here versus your I-beam. Just drawing freehand here, just don't judge my drawing skills. I don't identify as an artist. Yeah, we're ways there. So the amount of mass here that you have from your center is a lot more, even though it's the same weight. It weighs exactly the same. If we were to cut this part in half and you weigh this weight and that weight, they would both, let's just say 100 grams, just for argument's sake, just 100 grams, just for demonstration purposes. But because this mass here is further away from your center point, so this is basically where your crankshaft is rotating, because the mass there at that point is further away from your let's just draw a rod here, let's do it there. You have more mass in that line away from your center line. It is going to take a more effort to rotate that around, even though they weigh exactly the same. So the weight differs by less than that of a piston ring, but you will definitely be able to feel the difference in acceleration, not acceleration, a difference in throttle response on the I-beams versus the H-beams because of that mass that's there. So with an H-beam, this is better for, you want to move really fast, so what you want to do? RPM. That's your RPM application. This has a lot of mass there, so it's gonna be more reluctant to bend, so that's gonna be more power, strength. Well, not really power, because power is basically just has to do with tuning and everything. So this is going to be strength on that one, right? So a little bit of a science lesson there. But apparently people don't care about these things, so I'm just going to skip right over that. But that's the long and short of it. So people argue with me. If you want to run I-beams, you go for RPM. If you want to run power and boost, or strength, I've got to use the correct word, strength and boost, you want to go with the I-beams. So that is the long and the short of why you would want to go with your I-beam configuration compared to your H-beam. So I mean, if you basically add on the pistons, the gouging piston, that, and then the bearings on this part will weigh exactly the same as this part. I mean, this even has the ARP bolts, which I bet you are lighter, so this would actually from factory be heavier than this one. Well, I'm guessing I don't have the factory rod bolts for these, but yeah. So even though we have these, we have the ARP bolts on there, so in application, as the rods get to the top, the crank's going to pull that down. So your biggest force that you're going to want to be using is going to be that force pulling this down, because your piston is sitting on here. We've now made that heavier. This rod is about 16 grams heavier, so you've got more weight coming through. You do get, I think it's 625, 628 or something, and then the 2000. 625s are stronger if the same cross section is applicable. If it's not the same cross section, you can use the 65s to get into smaller, tighter spaces, so you can get with a smaller bolt a lot more strength because of that material benefits. And then obviously you have your ARP lubricant, which you got to use on the rods and that. And that's basically all the long and the short of it. If you compare your old rods to your new rods, fairly basic component, relatively elementary. You do need to obviously have a look to see if you have oil flow coming through there, which probably will require a special bearing. There are some guys that do like special patterns their bearings for better like oil cushioning and things, but if a force is applied to a liquid, the same pressure is applied throughout the liquid. So whether you got X's or crosses or squares or anything, it's not going to help unless you basically run out of oil starvation with the gauging pin is touching the with the bearings touching the crankshaft, and you will get that damage coming through from the friction. So yeah, so if you look at the rest of the designs, you have the same thing here. So you got all that mass in the center there, all the mass out there. So think of kind of like if you're trying to corner, you want to get the weight as low to the ground as possible. So with this one, you want to get it as far out. It's not really the same thing, but it's kind of the opposite, to give you more strength, something to compare to. So the further that is away from your center of rotation, the stronger your rod's going to be, even though they weigh exactly the same. I kind of do wonder if the bottom caps are the same. One thing I also want to point out here is if you look at your surfaces here, notice how this one has a little bit of a lip there and this one doesn't. So that's for your clamping surface. Obviously you've got a different metal here, which is of a higher quality, but you've got a more circular thing. So you actually get something that's called stress flow, which means as this has a force being applied to it, that stress is kind of going to press on through here, and flow follows the path of least resistance. Same with current, same with water, same with liquid. And it's going to find out, if you actually look at the boost line application, the boost the Vesseco boost line, they actually have other shapes here that sort of counteracts that stress flow, almost like the roots of a tree almost, where you kind of control where it goes. You can't really stop stress flow, you just kind of control where it goes. And then you still got to get into stuff like grain growth, but obviously, you know, we're not going to be able to analyze that as enthusiasts of engine builders and things. That's more for the manufacturers. They're going to look at grain growth, they're going to look at crack propagation, anything with a sharp. One thing I actually wanted to point out on that topic, crack propagation. If you look at all the corners here, everything has a nice fillet or a chamfer. There are no real sharp corners or jagged edges. You still have that little chamfer there. So that chamfer actually is important. It actually helps with oil flow, or retaining of oil flow, basically. Because that's going to sit in between the crank in there. So that has the function of, you know, keeping the oil in there. The bigger this band is, the more friction the oil is going to have inside the rod, the harder it's going to be to flow out. Comparing that to this one over here, which is our factory rods. I don't want to scratch the surface. Notice how much thinner that surface is there compared to that surface there. That's because, you know, with these ones, you've got that bigger seal against the crank, so your oil is going to be retained a lot better. You've got sharp edges here, sharp edges there, almost 90-degree edge almost there. I bet this can even cut my gloves if I pulled it over there. You have your corner pieces there. These are all stress concentrations. Now, stress concentrations normally form in the corners of components, and that's where cracks normally form and things basically progress. But yeah, we're already 15 minutes into this video. I wanted to make a quick video about the rods. They're a straightforward component. You also have to factor in your rod length. We're probably going to be digging into piston speeds later, but obviously Engineering Explained has a great video on piston speeds where your rod length of your, I don't know what the rod length is, the rod where that basically gets paired with your crank, and obviously higher RPM, lower piston speed, piston velocity, so it affects your flame speed, which your flame speed runs about 43 meters per second. And obviously, you know, you can calculate your vertical up and down acceleration through your crank size and everything, but I feel that's a bit overkill for what we're doing here. We're not going to be changing crankshafts and things like that, although I know on the 4G63 that is a very good thing we can do. We can actually, you can actually reduce the rod length on the engine and increase your crankshaft rotation, which increases your RPM. And I have seen guys pull 10,000 RPM out of a 4G63. It's not unheard of. But yeah, guys, so that's basically the long and short of it. We're probably going to finish up this video here. It's getting dark. I'm losing daylight, and battery's going to be dying soon as well. So that's the little buyer's guide on the rods. Just to recap, if you want to go for high boost applications, you want to get an I-beam. If you want to go for high RPM applications, you want to get an H-beam. I see too many guys putting H-beams in high boost applications, and they're just not pushing it for RPM. So do read up on your build. If you're running like a what's that Honda engine, so K20A, if you want to run a K20A, you probably want to go with the H-beams because you want to get that RPM, you want to get that revs, you want to get the kilowatts. And if you're going to go with like a boost application, so like a 4G63, 4B11, 2JZ, RB26, you probably want to be going with I-beams because they just have that added strength and that. So hopefully now you guys will be able to look at con rods and know which ones are better, which ones are not. You can even see like there's a little cavity there for oil to escape out there, where this one does not have that. So this rod is not directional, where this rod actually is directional. So look at the positioning where they're sitting. It does kind of matter where which way you put them around. Are they directional? Am I talking nonsense? Well, unfortunately it's a bit dark now, so I can't really see. But normally you'd have a rod with a chamfer on the one side, not the other one, which will point to the front of the engine, or there'll be some indication. These rods are symmetrical, whether you put them this way or that way, won't matter. There are no indications, so we're just going to use the logo as our indication, and that's going to point to the front of the engine in that configuration. The blank side's going to remain to the rear. So that's one thing to look out of the direction of the rods, and that basically covers it. So guys, I've got to finish up here. It's getting dark, and I will probably do the piston assemblies tomorrow then. And then I'll see you guys then. Thanks for watching. Have a good one. Yeah, strength of the community, I guess.